All right, we're starting a new unit, and to begin this unit 5, I kind of want to go over a big concept, a concept called interdependence. Interdependence is actually one of the 3 main themes in biology, and it looks at how everything is embedded, entwined, interrelated, integrated together within systems, parts of systems, and the environment as a whole. That not one piece can survive without it on its own. We need all the other pieces in place to exist, and those other pieces need us to exist. So that's what interdependence is, and the best way to represent that to you is with these 2 processes: cellular respiration and photosynthesis. And we're going to, in a couple other videos, look at those individually. But here's a great graphic by the Amoeba sisters that lets us summarize how those 2 formulas, those 2 equations, are interdependent. When we look at cellular respirations, that is the process that your cells use to get energy. We have to breathe in oxygen, we have to eat sugar. Well, where does that oxygen come from? We'll look at photosynthesis. Oxygen is a waste product of photosynthesis. It comes from plants. We breathe in their waste product, and we eat the sugar that they make. In turn, plants require carbon dioxide and water. Well, where do they get that from? They get it from cellular respiration as waste products. Carbon dioxide and water are our waste products. So that's showing you how these 2 equations need each other, that these molecules come from somewhere, they're going somewhere else, they're needed somewhere else, and then they're moving back through to a different place. And that's why we were focusing on those biogeochemical cycles, because it's showing you how those molecules are moving through systems. So we're going to review the water cycle, because that's the movement of water. And remember, both those equations have water. We're either breathing it out as water vapor, or the plants are pulling it up through the roots as a liquid form. But remember, water moves through systems. It's cycled through. It's never, it doesn't just go away. It's there, and it's one of those key pieces to both the cellular respiration and photosynthesis. Carbon dioxide, again, another key piece to both of those processes, that it has to move through these systems and push its way through and cycle its way through, so that both of those equations can take place. So when we put that together and we appreciate that, okay, I got these molecules moving through, the piece that's missing is energy. We need chemical energy, ATP, in our cells to do work. Plants do too, but they also need sunlight to start this whole chain reaction going. So all life on this planet depends on the sun. And in the next few minutes, we're going to look at how that energy from the sun moves through systems. So first of all, we got to get the sunlight, okay? We got to catch the rainbow. And the organisms that are going to let us do that are the ones that are called autotrophs. Those are plants, okay? They get their energy directly from the sun. They can convert it to usable forms, and they're able to make their own energy. Heterotrophs are organisms that cannot make their own energy, so they get their energy from the sun indirectly. So we can also refer to autotrophs as being producers, because they're producing their own energy, and we can look at heterotrophs being consumers, because they have to consume their energy from actually other organisms, whether it's a producer or eating another consumer. Now I can represent that energy movement by using a food chain. And to do that, we're always going to start off our food chain with a producer, because that's the one that's making the energy available in some chemical organic form. That producer then will be eaten by a consumer, typically an herbivore. And then as we move through, and the arrows show the direction the energy is moving, that consumer will again be eaten by another consumer, which will then be eaten by another consumer. But it shows a linear pathway of our energy going from producer to consumer to consumer to consumer. Now in comparison, where I have the linear food chain, I can map out several different food chains, and then I can show how those food chains can all be distributed in different ways. Maybe it's not a straight path to get to the owl. Maybe there's several paths to get the energy to the owl. And that can be represented with a food web. So a food web looks a lot more complex because it's showing all the possible food chains, all the possible ways that the energy can be moved through that system. Where the food chain is just showing a single relationship, a single pathway, a food web is going to show you all the possible pathways in that system to move the energy through. So, if all life on Earth gets its energy from the sun, then how do we actually receive that energy? Well, the first process, the main process, has to do with those producers. They are going to use photosynthesis or another version called chemosynthesis. Chemosynthesis is a little different than photosynthesis in that they're using the chemical energy, radiant energy around them in their environment to convert to organic molecules, to convert it to a different form of energy, where photosynthesis, they're using direct sunlight to create organic compounds that we'll use as energy, like the foods that we eat. So that's how it initially starts. Consumers then will eat a producer or another organism and then get their energy from that organism they just consumed. And we'll go break it down through into their digestive system, get those molecules available to the cells and tissues, and then they can enter the cells for cellular respiration. There's different types of consumers. There's herbivores that just eat plants. There are carnivores that eat only meat. Omnivores are kind of like the garbage eaters where they'll eat plants, animals, whatever. And then there's detrivores. Detrivores are like scavengers. They eat dead animals. So it's like an animal eating another dead animal, which would be like a vulture. And then your decomposers are your microscopic organisms like bacteria and fungus that break down dead things, organic matter, into molecules. So those are different types of consumers. So now that we know that we got producers making the energy for themselves or others, consumers eating or getting the energy from producers, how is that energy actually being transferred from organism to organism? And we can think back to our food chain, that we're going to start with producers. We're going to start from the sun to the autotrophs, and then we're going to have a primary consumer, and those are going to be the ones to first consume the plants. Typically those are going to be your herbivores. And then we're going to have a secondary consumer who is then going to feed upon the primary consumer. And then lastly we'll have what's called a tertiary consumer, and they're going to feed upon other consumers. And so that's typically how the energy transfers from one level to the next. We have producers to primary consumer to secondary consumer to tertiary consumer. So I can organize an organism's position based upon where they're at in the energy transfer, and I do that by placing them in a certain trophic level. And when I hear the word trophic, I think of trough, like a food trough. Okay, what's your place at dinner? Where are you going to eat? And so producers within this energy pyramid make up the base, because they are making the energy. They are the foundation for the available biomass for all the consumers above them. So they get the bottom, because they're building this pyramid. And then you can see that the primary consumers are the first to eat after producers are there. Then we have our secondary consumers are going to be the second ones to eat. And then our tertiary consumers are going to be the third ones to eat. Now, a lot of kids get those positions and within the trophic levels confused with the name within maybe the food chain. And so try to keep it clear that a primary consumer is probably a plant eater. It's an herbivore. That a secondary consumer is going to be a carnivore. Now, because they're eating first over here in terms of carnivore, they're going to be a primary carnivore, even though their position at dinner at the trough is secondary. And then you have your tertiary consumers are going to be your secondary carnivores because they're eating the other carnivores or they're eating the other herbivores, but they're second to these guys, but they're third at dinner. So try to keep that clear in your head and know that difference. Now, when we look at energy transfer, the question is like how much energy is actually being given or passed on to one trophic level to the other, and the answer is not a lot. It's only 10%. If somebody was to engineer and design this to be like, wow, that's horribly inefficient, and it is. Only 10% energy makes it from one trophic level to the next. But then at the end of these transfers, we're done and we're out of energy. So for comparison, when we're cycling molecules, matter, like the water cycle, carbon cycle, those cycles continue. They're ongoing. Energy transfer is linear. It starts with the producers, it moves itself up through the three consumers, and then we're done. Because if you can see right here, there's nothing left. Okay, there's only so much available energy, and then when it's consumed, it's gone. Which would make sense. That's why you have to keep eating. If you were cycling your own energy, you wouldn't have to eat. Well, we got to keep eating because we use our energy and it's gone. So if I look at that in terms of calories, here you go. Say I have 1,000,000 calories of sunlight. Well, 10% of that is 10,000 calories available to my producers. Well, now my primary consumers, which are herbivores, get 10% of that. Well, that's just 1,000 calories. And then we can look at my secondary consumers get 10% of this. Well, that's 100 calories. And then my tertiary only get 10. And 10% of 10 is 1, and 1 calorie ain't going to do anybody any good. So we're out of energy. We're done. So there's a limit to the number of trophic levels. And typically it's about 4. So that we only have about 4 levels of passable energy, and then we run out. We're done. So why is it so low? Well, not everybody gets eaten. If they did, we'd have extinction. So obviously some things escape. The next one is the energy that the prey that is being used for their own body, their own self through cellular respiration, can't be passed on to the predator. So that energy is not available to the one who's eating them. We're just going after the molecules that make them up. The next reason is we don't eat everything. If you have steak, you're eating a section of the cow. You're not eating the whole cow. And so what would be available in terms of hoofs, horns, hides, we're not consuming that. It's not tasty, and who would want it anyway? And then no transfer of energy in any system is ever 100% efficient. So that's why it's so low. So hopefully this begins your understanding of how energy is moving through the system, how these molecules play an important part. And again, we're going to follow up more of that with our next videos in photosynthesis and cellular respiration.